Good afternoon or good evening, and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. We're very excited to give you yet another report of the Mars Curiosity rover and its activities for Sol 1. Let me introduce the panel that will talk to you today. We have, first of all, Jennifer Trosper. She's the Mars Science Laboratory Mission Manager. She's with the Jet Propulsion Laboratory. Michael Malin, the Principal Investigator for the Mars Descent Imager, and he's with Malin Space Science Systems in San Diego. And Joy Crisp, the Deputy Project Scientist for the Mars Science Laboratory mission. She's also with the Jet Propulsion Laboratory, and we will begin with Jennifer.
Good morning. It's morning on Mars. It's Sol 1, and it's about 8 a.m. local solar time, and the rover is just getting ready to wake up for its first day on a new place. And before I talk about what the rover is doing today, I actually want to give you a little insight into what the team is doing, because I am just a representative of lots and lots of incredibly talented people who are busy doing a variety of things. There's a group of people who is currently they're building the sequences that we're going to send to the rover in about 2 hours to tell it to execute our pre-planned Sol 1 activities. So they're busily looking at the times and making sure that we're uplinking the data at the right time. We also have a team of people who've been busy in the surface MSA where all of our downlink data comes down. And the last time we talked to you, we had about 5 megabits of data on the ground. Now we have about 40 megabits of data on the ground, so we have some extraordinary stuff to talk about today that we got down from the rovers this morning Pacific time. So there are lots of people working hard, and I think what's extremely exciting is that the rover is in this new place and is going to teach us about this new landing site. And even though it's cool and crisp, and Earth has already risen like a star in the sky there at Mars, the sun is starting to rise, and about 9:45 local solar, the rover is going to wake up, which is about 5:45 p.m. today. When the rover wakes up, we're going to do kind of two critical things today. We're going to check out the high gain antenna, and I'll talk to you about that a little bit, and we're also going to do some instrument health checks. Now, the reason we want to check out the high gain antenna is because we want to make sure we have as many communication links as possible. And I want to start with a video that shows the deployment of the HDA. So can you go ahead and roll that video, and then I'll talk to the model. So here you see the rover. Actually, you'll see that the remote sensing mast is deployed, which is not the current state of the vehicle. But here you'll see when the pyro fires, there's a spring release mechanism that goes, which happened yesterday on Sol 0. And then the HDA deploys and moves and points towards Earth. So that's what we're doing this morning. If you go on to the next slide, I want to talk a little bit about the communications links that we have. So there you can see Earth, and you can see the rover there on Mars, and it's kind of like when my husband and I lived in the Mojave Desert, we like to have different cell phone carriers on each of our phones just in case somebody didn't have a tower in the area. So it's sort of like how we have Curiosity on Mars, where we have a relay. If you look, you can see that we relay through the Odyssey orbiter. And last night, Sol 0 in the afternoon, we relayed through the Odyssey orbiter, and we've also received another relay through the Odyssey orbiter early this morning, Mars time. We did receive a relay through the MRO orbiter early this morning, Mars time. And what we're still checking out is this direct-to-Earth link on the rover that can be through one of two antennas. So let me show you on the model. We have a low-gain antenna right here. It's just a post, and it's an omnidirectional antenna. And as long as we have enough of a strong signal from the ground, so we use the 70-meter dishes with the strong transmitters, we actually can uplink to this antenna regardless of the orientation of the rover, as long as Earth is above the horizon. So this morning on Sol 1, we'll send a command into the low-gain antenna. That command is going to start the activities for the day. And one of the activities is going to be to deploy this high-gain antenna. And then as Earth rises, the high-gain antenna, based on our information about the clock angle of the rover, which we believe to be about 112 degrees from north, which is why I put the rover here. If you assume that is north, then this is about the orientation we think the rover is at. The Earth will rise. The high gain antenna will track the Earth from about 11:45 local solar today for about 75 minutes. And if that all goes well, then we will have established that we can send commands on our low gain antenna, and that we can receive commands and also send data on our high gain antenna. And so we will have confirmed that all of our communications links work perfectly, and that would be fantastic. That's one of the main engineering objectives that we're trying out on the first few sols. So if you go to the next slide, this is the front HazCam image of Mount Sharp, and I believe Joy is going to talk about this more, so I'm not going to steal her thunder, but we'll talk about that a little bit more. So go on to the next slide. Okay, so I want to talk about the specific things today. We'll do the HGA deploy, we'll track Earth. We're also going to exercise the RAD and the REMS instruments. So as far as instrument health checks go, we've used the Marty. You'll see some Marty thumbnails. We have also used the ChemCam because we wanted to put it in its sun-safe position on Sol 0. On Sol 1, we will use the RAD and the REMS and do their checkouts. And then through the next few sols, we'll finish with the mast cam. We'll also do the nav cam. We will take an image of Molly, and I want to talk about the Sol 1 Molly image today. And then we will do SAM in a couple sols. So we'll talk about that. But let's go to the next slide to talk about the Molly Sol 1 image. So another reason I put the rover in this configuration is because the robotic arm is still stowed, but we are going to take an image with the Molly while the arm is stowed. And what you see there is the field of view of the Molly while the arm is stowed. And if you look at the orientation, the clock angle of the rover at about 111, 112 degrees, the Molly is about 110 degrees facing this way. So we're going to get an image almost directly north with a 15-degree field of view of the Molly image, and we would expect that to come down in the Sol 1 PM pass this evening, which you'll receive the data about midnight tonight. So that's the exciting stuff for today. If you go to the next image. Now you saw this morning, and we're going to scroll down a little bit because we saw something else in this high-rise image later, which we believe to be the heat shield, which then leads me to introduce Mike Malin, who's going to talk a little bit more about some other images of the heat shield.
Thank you, Jennifer. First of all, I feel sort of compelled to point out that this press conference is occurring 12 years and 8 months after when I had originally thought I'd be telling you about these types of images. I had a camera that was going to do this then, and this is the first time I have a chance to tell you about those images. Also, 11 years and 8 months from today, in the past, Ken Edgett and I were on this podium telling you about Gale Crater and why it would be a great place to go examine sedimentary rock on Mars. So I'm very excited about being here with the here being on Gale, because I project myself out to the vehicle. And I think of myself as it's my surrogate, but it's sort of like my student. I've got to tell it what to do. So I'm going to tell you a little bit about the Marty descent sequence. You may remember, for those of you who saw the briefing a couple of days ago about the descent imaging system, we take images for a very long period of time. The EDL took much shorter than had been the longest it could have taken. It was only 100. We took images for 158 seconds, 159 seconds, and we take frames at about 4 frames a second. So there are about 660 images that we acquired while the vehicle was in the air. And then we have a whole bunch of images that were taken after the vehicle landed. We sampled those in a very widely separated time frame in order to make sure we got everything. So we got something like 12 or 14 frames initially that were in the air and 6 frames thereafter. And then we started having the times, and we ended up with about 220-ish frames that I'll show you in an animation a little later. So the sequence began with the camera turning on about 6 seconds before the heat shield jettisoned. Those images will be black, but then we'll watch the heat shield fall away at 4 frames per second. So we'll see it in a very nice, it's an engineering experiment just to watch it, but the pictures are very pretty. And so if I could have the first slide, that's the heat shield looking as you look down at Mars, and those are, you see the big white patch is our calibration target, which allows us to adjust the brightnesses. It's a shame that we really can't reproduce the color for you really well right now, but on these thumbnails, they're pretty highly compressed, and they're very small. The images are only 192 by 144 pixels across, JPEG compressed. Those of you who are familiar with JPEG know you can really do pretty much damage to your pictures by doing too heavily compressed. But we have a sequence of these images, and you'll see those in the animation a little later. But there you see the dune field, and when the full resolution image comes back, obviously up to the upper right corner of this image, you will see the mound, as you saw in the HazCam image. So this image was taken about 2 minutes and 30 seconds from touchdown. The heat shield was about 15 meters away, just a little over 50 feet, and heat shield is about 4.5 meters across, to remind you. So this is what it looked like as it was falling away, and you can see that the high-rise images certainly looks like this too, so clearly they captured the heat shield falling away. The next single frame, this is basically a sort of a mid-altitude image. We don't have the exact heights yet because we have yet to correlate our observations with the EDL team's observations with the radar. But as you'll see in the animation when I get to it, you'll see the vehicle sort of nodding up and down from while it's on the parachute, and you'll see it make some fairly major turns as it powers on the main rocket, main landing engines. And this is just one we took sort of randomly in that sequence that showed craters, shows the sand dunes. So we're sort of in a position here of turning around and heading down for the landing. This was taken about 1 minute 16 seconds from touchdown. The next one shows that we picked up some dust, and when I'm narrating the animation, I'll try to reproduce the Buzz Aldrin comments from from Apollo 11, but we picked up dust, and this is the only one you're going to see really clearly. So so you can see this is the first image that showed dust. An image taken 1/2 second earlier than this was not showing any dust movement, and so the engines impinged on the surface at a very specific time. This is about 20 meters above the surface probably, and you can see it's elliptical. It's not circular. That's because the shape of the engines, where the engines are around the vehicle, gave it a wider dispersion in one direction than another. The next slide, I think, is just going to be pictures that we took on the surface. The exposure time for our images was very short, 0.9 milliseconds. So that's 9/10,000ths of a second. We did that because we were afraid that the vehicle would be vibrating and oscillating. We need to stop the action. When we got on the surface, we were in shadow. You can see a strip of light which is shining through some materials. The vehicle has a certain shape. Light was shining through that shape, illuminating the surface. So we do see lots of rocks on the surface that we can correlate with things. And I'll talk a little bit about the correlation. Actually, I should do it now because I'm going to show the video. I'll probably stop with the video. We actually know where the vehicle landed by matching features that we saw in the descent images to the high-rise mosaics that we had. So it landed at -4.5895 degrees, so that's 4.5895 south, 137.4417 east. It's oriented at north 114 east. So we are able to do that by matching features that we saw in the in the hazard cams, the HazCam images with the features that we were seeing, and also knowing the laser altimeter from Mars Global Surveyor's geodetic network. So we really we've pinned it down in these extremely low resolution images, probably to about a meter, which is much higher resolution than we can do with the overall network of Mars for longitude and latitude. And when we get the high resolution or the full frames back, we should be able to tell where the vehicle is to within centimeters. We don't really need to know it that well, but we should be able to do that. So I believe the next thing that should be queued up is the video. I don't know what that was. That looks just like dust plume, or that's the wheel. That's actually the engineering also. That's the first image that the wheel showed up in. So you see in the lower right corner, that image is actually upside down. You can't really tell that, but it's upside down because the wheels, as we take the image, is in the lower right corner. So I usually flip everything so that the top of the camera is in the direction that the vehicle is facing. So that's we watched the wheels deploy. It came in very quickly. When we touched down, it moves a little bit out of the field of view because the weight of the vehicle on the wheel pushes it out a little. So, and it's a yardstick we can use to measure where we are. And obviously on the surface, we can watch the tracks and do some science with that. So I guess now we're ready to go with the video. And it'll start with a stop on the heat shield, and then it'll start moving. So there they are moving away. I call this stop action because it's really individual frames. We've done no modification of the frames to get them to line up or anything. You can see that it's basically facing to the top is to the east, and the dunes have left the upper right part of it. We're zooming around, turning. Some of that large motion you just saw was probably the divert maneuver, and now we're coming close to the surface. There's the dust down at the surface, and lots of dust, picking up a lot of dust, Houston, and and it'll stop pretty much when we get to the surface. See the wheels in the upper left there because it's the front left wheel. So I'm looking forward. Thank you very much. I really hope you'll stick around. At some point, we'll get the full frames back, and that video will just be exquisite in full frame. Towards the end, we'll be seeing things only a millimeter or two across in the final frames, and we'll be able to track the dust and get some idea of the velocity, the impingement force of the plumes. There's a lot of sort of exciting engineering and science we can pull out of the MARTI, and hopefully we'll get those out to you in the near future. Joy?
All right. So I'm going to start with a video. This is a video that was put together by Doug Ellison. He used elevation data from high-resolution stereo camera that's on Mars Express, together with image data from the context camera on Mars Reconnaissance Orbiter, and color info from Viking. And so you get to see where the ellipse is, where we landed, and if you were standing there looking around, getting a nice panoramic view, just all animated, but it just nicely shows you going from Mount Sharp, and now looking at the rim, as if you could pan around. So eventually we'll get to do this with our own cameras, but for now this is a very helpful tool for scientists to get a feel for where they are and what it is around them. And then we can put that into context now, having just gotten this full resolution hazard camera, which so fortunately is pointed right at Mount Sharp. So we can see the top of it. Once again, to remind you, this is taller than any mountain in the lower 48 states. So it's pretty spectacular. We're currently, when we look at Mount Sharp, that is 22 kilometers away, or actually it's 28 kilometers in the direction of this camera. And it's, get that number wrong, it's 6.5 kilometers to Mount Sharp. It's, we'll have a later view of the rim. That's what's 22 kilometers directly away from us. This is geometrically corrected. So you've seen a lot of fisheye camera views from the hazard cameras, and this one's straightened out. So this has been corrected. We can see more clearly these little pebbles all over the ground. We can see a little bit better than we saw yesterday that it's very flat. We're not sure how easy it is going to be to scoop this kind of material if we do end up trying to scoop it. You can see that the wheels have not sunk into it. And we were struck by how the size distribution of these pebbles is relatively in a restricted range of up to a few centimeters. So what catches your eye are the dark dunes that are piled up along the base of Mount Sharp. We have seen more detail in Mount Sharp itself from the orbital images, and so we are looking forward to getting some other images like Molly and mast cam and driving over and getting a closer look. But for now, it's just very reassuring that we have in front of us, we can drive. There are no obstacles for driving, and we have the ultimate goal of the mission to eventually get over to Mount Sharp. Also, I think it's fun to see that you can see the silhouette, the shadow of the rover in much sharper detail than you could yesterday. And the next image, first we have an animation of just showing you where the rear haz cams are, the field of view that they can see. And then thank goodness we had dust covers which deployed, because now we know there definitely was a lot of dust kicked up. And so this is the full res view from the left rear haz cam now with the dust cover removed. And you can see the wheel of the rover, and again, very flat with these pebbles and no obstacles for driving, so we'll be able to drive front or rearwards. And from this vantage point, looking to the rim of Gale, it's the northwest rim that we're looking at, and it's 28 kilometers away from us in this direction. So that's all I wanted to share.
All right, we'll open it up to questions here at JPL, and just wait for a microphone to come to you. We're going to start over here and then go on that side, right over here in the middle.
Is it the front? Just quick. Is it the front haz cam that showed the picture of Mount Sharp?
That's correct.
Okay. So it's facing Mount Sharp.
Yes.
All right.
Okay, then let's go to this side. Yeah, wait for the, okay, go ahead, Eric.
Okay.
Yep.
Hi, yeah, Eric Ham with Nature. Quick question about this image right here. It looks like there's a line below the crater rim. Is that an intermediate feature of some sort here?
I believe that's just the local horizon. Tim, do you want to chime in, or Mike, you want to add to that? I mean, it's the local horizon that we're seeing.
Then what's above it then?
Then that's the rim of the crater, the wall of the crater behind it. So you're seeing you're just seeing, this is a 120-degree fisheye view, and you're seeing that the edge of the horizon is the first line that you see there. But
That's
beyond
that's
that,
probably only a few hundred meters or closer.
but then way
then
beyond that,
beyond
you're
that
seeing
is-
the wall of the crater rising up.
Okay.
Kelly Beatty, Sky and Telescope. Joy, do you expect the hematite concretions, the blueberries, to be on this surface? And does their presence or lack thereof tell you anything about how the deposition might have taken place inside Gale?
Well, from our orbital imagery, orbital data sets, we're not expecting to find hematite berries. They could be present at an abundance that we can't detect from orbit. But basically, you know, Meridiani was an unusual location on Mars where this hematite signature was seen from orbit. And this is, we weren't expecting to see that here. We don't see highly rounded grains that like we've seen with Opportunity. So we'll find out especially when we finally get a sample into ChemIn as to whether there's hematite. Now, there could be hematite in the soil that's not in the same concretion type forms. So actually, I'm going to take back a little bit of what I said. We would expect some hematite in the soil, but not the hematite concretions necessarily, or high abundances.
Go ahead, John.
John Johnson. I don't want to be a wet blanket or anything, but I mean, everything seems to have gone so perfect on this. Is there anything that hasn't gone right? Anything you're worried about right now?
No.
Thank you.
I'll add to that. There are certainly a lot of things that have to continue to go right. We have a fairly complicated transition from our, what we call the R9 version of flight software to the new version that has some more surface capabilities. As soon as we get our communications links checked out and all of the instruments to be just aliveness checks, we're going to start on that transition around Sol 5. And we're going to do that on both RCEs, and that's going to take about 4 sols, and there's a lot of interaction between the ground and the vehicle during that. And it's a fairly complicated activity. So we have things, and you'll note that we still haven't unstowed and deployed the arm and several things like that. So there's a lot ahead of us, but so far we are just ecstatic about the performance of the vehicle.
Jennifer, could you tell us what the acronym RCE is? I don't know if you said that.
That's the computer. Don't ask about RCE, just it's the computer.
Okay, go ahead.
Hello, Olivier. Oh, don't work. Yes, it works. Okay, sorry. Olivier Sangui from EnjoySpace.com, France. I would like to know, a lot have been said about the dust on the solar panels. Of course, Curiosity does not have this problem, but dust can be a problem for the cameras. Could it be lowering the performances, for example, having dust on the optics with wind blowing, etc. on Mars?
Sure, and we have experience with cameras on like Spirit and Opportunity, right, which were even lower to the ground. So our biggest fear was the dust kicked up during entry, descent, and landing, that would be a problem. So we did install these covers on the hazard cameras, which are the lowest to the ground. With Spirit and Opportunity, as time goes along, the wind blows, electrostatic charging conditions change, so we've seen dust come and go and not just build up thicker and thicker. So we expect to have similar behavior and hopefully better luck having the cameras higher up off the ground, but it remains to be seen. It can be a concern.
Okay, we're going to the back of the room here. There's the microphone.
Thank you. What can you tell us about the temperature and what the robot is encountering weather-wise?
I don't have any numbers from, do we have data from REMS at this point?
No.
We don't have data from the meteorological station, the REMS station yet. So all we would have would be predictions. And I don't have those numbers at my fingertips.
But we will get the REMS data tomorrow. We'll get it early in the day, and then we'll also get it at the landing time so that we can correlate with some of the Sol 0 information.
Okay, here in the middle.
So this might be a silly question, but from covering the Spirit and Opportunity, when we wake up one of those rovers back in 2004, it was waking up because it had to wait for the sun to rise because those were solar powered, right? So, and this is a nuclear powered rover, I thought. So, why are we just waking up? Like, shouldn't the thing be running kind of around the clock, or?
Yeah. So yes, we have
Oh, you already asked that question.
a radioisotope thermoelectric generator, the RTG, which you can see here. Puts out about 100 watts. We also have a battery, 80 amp hours-ish, that stores energy. However, when we want to operate the vehicle, it's 135 watts or so. So we can't actually operate the vehicle simply on the 100 watts from the RTG. So when we power on the vehicle, we start to take energy from the battery. And so we actually have to manage the battery energy fairly well, and sleeping at night helps us do that. We have survival heaters. And additionally, it's so cold at night, there aren't that many things we can do without heating up actuators and using a lot of energy. So the RTG certainly helps, but it doesn't keep us from having to manage the energy balance every sol.
So this thing's not really around the clock workhorse, where it's, a nuclear power, so you can go and explore during nighttime. That's not going to happen, right? It's still gonna
We still have to have we have about 2,080 watt hours that we can use every sol when you combine what the RTG puts out and kind of an energy balance with depleting the battery and recharging it completely. Now, once we start to characterize the system, we will potentially, move that number up a little bit, but that's our constraint, and so you have to plan things. So you can stay up in the middle of the night, and you can be up for a few hours, but you still have to stay within your 2,000 watt-hour constraint. Yeah.
Okay, Craig, you had a question? And then we're going across the aisle. Yep.
Hi, Craig Cavalt with America Space. I think for Joy, the picture there of the Mount Sharp, the tone of the mountain was quite light or whitish, and I don't mean to describe it as snow, but is that an accurate characterization at this stage, and if so, what would that mean?
I actually don't know. The funny thing was I got to work and almost all the scientists had gone to sleep. So I was scrambling to work on this myself. Had some help from image processors, and they were trying to do a lot of stretching, and I believe it was stretched so that you could see a lot in the foreground. And so I wouldn't put a lot of weight yet on the lightness, the tone of the mountain until can get some info from the experts. So I'd be hesitant to say, yes, it looks like snow. I'm not sure. So it probably was stretched that way.
Go ahead.
Good afternoon, good day in Mars. I'm Fernando from Tercer Milenio in Mexico. Then, if everything is fine in the Curiosity, when will they start the first experiments? The use of the drill, the laser, the mass spectrometer, the search of the life. When?
Soon. We really need to get to our new version of flight software first. So I would say that's the main constraint we have right now. And it looks like we're on the path to starting that on Sol 5. It takes 2 sols, so Sol 5 and 6 to do the primary computer, and then it takes 2 sols to do the backup computer. So by Sol 9, we'll begin doing the higher level characterizations required to do some of the more exciting science that you're talking about.
Thank you.
Okay, we'll go on the other side of the aisle here.
Hi, I'm Evan Ackerman with IEEE Spectrum. What is going to happen to the MARDI descent imager now? Is it completely finished, or is there anything else you can do with it?
We have plans to try to use it on the surface. Obviously, we can't point it. It goes wherever the rover goes, so and it points down. We have a plan to try to collect a sidewalk size. A field of view is about the size of a sidewalk, and basically drive a sidewalk view of the surface as we drive towards the Mount Sharp. It's a little difficult to do that because it has to be coordinated with the drive, and the drive is a very complicated thing. It has a very exotic cadence. It drives a little, it stops a little, it drives a little bit more. Commanding the camera to do that is very difficult, so we could either have the drive commanded to do that, or we could start the camera and then take pictures while it's driving for the whole amount of time. The problem there is that most of the images won't show any changes because it drives in this sort of stop-start manner. We'd never be able to get all the thumbnails back, let alone full frames. But the intent is to use it. It's got probably, it's nowhere near as high a resolution as the Molly is, but then the Molly's on the arm and doesn't actually look all the time. It's probably comparable to what we could do with the mass cam, but you don't really want to run the mass cam while the vehicle's driving because the focus mechanism, you might damage it, so you want to stow the focus mechanism. So all we could take would be out of focus images. So Marty has a role, and we're still exploring that.
Okay, we're going to Irene next, and then you, and then we're going to the other side of the room. Go ahead.
Irene Klotz with Reuters for Dr. Crisp. On Earth, typically what is responsible for forming little uniform pebbles and gravel like what you see in this picture?
Good question. I'm going to take a stab at it, and then I'm going to let Mike help me. I would say, did you?
I didn't need to hear the...
Okay, so her question was, on the Earth, what would be a typical way to form this pebbly surface? And I would I'm going to make a
something I know.
guess at it here and just say, we know that Gale Crater was filled in with sediments, and then a large quantity of material has been eroded away. So you're seeing what's left after a lot of erosion, and rock that was once there has been broken up by physical processes, freezing and thawing, and wind, and other ways that it can break it down into little pieces. Now, why it's all these small pieces, I don't know. I think the science team has a lot of work to do to figure out how were these materials put there. You know, was water involved? We don't know yet. Mike, do you want to take a shot at it?
Yeah, this is obviously a lag deposit. That means it came in with a bunch of other stuff, but this stuff is not able to be taken away. The finer materials have been removed from this area. The fact that there aren't a large number of bigger things is more interesting to me than the fact that there isn't a lot of small things. Small things winds can transport. Big things, you have to break them down to get them small, and this is probably potentially impact ejecta, but I'm surprised there aren't larger fragments. This is actually something that me and my team are very interested in, trying to understand what causes this type of surface to develop on Mars. There is a possibility, probably pretty remote, that it's not unlike the materials concentrated at the Meridiani site, in that these may be fragments that were in material above this surface and have been lowered down as that surface was eroded away. And Joy was also alluding to that. So this type of surface is very familiar to people who work in deserts. People go off-road biking and things like that. So this should look pretty familiar to them.
So actually, just on another note, I wanted to clarify something I said about how soon we're going to do things, because I was actually speaking to firing the LIBs and the RMI in the Sol 10-ish timeframe. We were speaking earlier about how Curiosity's middle name might be Patience, because it does take time to check out the vehicle. And so drilling is not something that we're going to do until, it may be a month before we're able to drill, because we have to set up the parameters on the arm, we have to deploy the arm, we have 6 sols of checkout of the arm to make sure that we understand how it's behaving in this environment, how it survived the landing. So just didn't want to give you the wrong impression. It's going to take a while before we're ready to drill.
Okay, we'll go ahead over here now.
Hi, Nadia Drake with Science News, and this is for Mike Malin. You might have mentioned this, but I might have missed it, but when are you expecting the high-res video to be ready, and is the thumbnail version posted somewhere that we can see?
Thumbnail what?
Is the thumbnail version posted, and when are you expecting the high-res video to be ready?
The images that I showed will be posted on the JPL website. I believe also the animation will be. The animation itself is actually, I believe, a motion JPEG, so you'll actually have all the frames are combined in that animation. We will get around to doing the raw frames, but we've been going back and forth with JPL about how to get stuff on their cloud server, so that's been an issue for us. They'll be available pretty soon. Now, your earlier question was?
When is the full resolution video going to be available?
Don't know. Right now, we're not really planned to see many of the full frame images till a couple of weeks from now. When we start seeing them, we will get a few full frame images over the next week. There should be one queued up for coming down, I guess, tomorrow morning. Tomorrow morning will be remember the image in the movie, there's a close-up view of the heat shield, and then the very first frame after that was a little heat shield. That image should be queued up to be coming down first of the full frame images. Then over the course, I think sometime around Sol 4, we reprioritize the remaining 17 of the first 18, so I expect Sol 5, Sol 6, we might see those. I don't know much about what the downlink for the software load, whatever, the reload, the new load for the software. I don't know exactly what the the downlink part of that sol is going to look, those sols are going to look like. But it's in that time frame we'll start getting individual full resolution images. And one could make an animation probably a much better resolution than this one, just from a few separate full frame images, because they're 8 times higher spatial resolution than the thing. So it's going to be a couple of weeks before we really start having the pieces for it.
Leo Enright with Irish Television. Curiosity is a word which news reporters understand, but we don't understand patience. So I was just wondering, there was a lot of talk at one stage about an intermission, which seemed to be some sort of a period when you'd actually do some stuff and then get back to doing some, engineering. So I just wondered if you could talk to that, and also just briefly, more I think maybe for Veronica, but there's a lot happening tonight, particularly the LGA X-band at 10:50 Mars local, and then about an hour later the HGA deploy and a signal from that. I mean, are we going to have live feed out of the control room for that or not?
I can answer that and say no, we aren't going to have a live feed tonight, but we are planning to be back here tomorrow morning at 10 a.m. Pacific time, and for the rest of this week at 10 a.m. Pacific time with updates. And there was another part to that question.
The intermission.
Let me take a crack at the intermission, because I'm one of the big pushers for that. The Mastcam has a lot of idiosyncrasies that we were not really able to test on the ground. The vehicle itself creates an environment for us, and pointing and things like that. So we asked for the intermission, and we asked to do a number of very specific things, including taking extremely high-quality images. None of this JPEG compression, really losslessly compressed, high-resolution things, following the effect of sunlight and shooting high-resolution with the narrow-angle camera mosaics of distant objects to do long baseline stereo observation, things of that nature. These are things we've never been able to test yet. We're not even sure our software is going to work. So in the framework of an intermission that was oriented towards trying to acquire stuff that would be of interest scientifically, but also addressing the engineering concerns that we had for the instruments, the concept of the intermission came up. And for the Mastcam, that's what we're going to do that. I believe ChemCam is also doing some similar tests of checking things. I forget, there are 2 other. Sam is going to, I think, is that what it does? It's atmospheric? Sam, I think, is going to make an atmospheric measurement, which would be very exciting. So those are basically characterizing the engineering of these instruments while acquiring something that's scientifically valuable. That's Sol 10-ish starts.
Yeah, it's a couple weeks. It'll be 15-ish.
Okay, we have
now, don't forget the Mastcam takes the 34 millimeter Mastcam takes a 360 in color on Sol 4. And I think we see the thumbnails are scheduled to come down late in Sol 4.
Yeah, and keep in mind, I think the Sol 3 Mastcam and the Sol 4 ChemCam images are going to be coming down during the flight software transition on 5, 6, 7, and 8. And then we're doing science. After that, we're doing all of the higher level science checkout and experiments. We just aren't fully, completely checked out on the vehicle because the arm isn't deployed and we haven't characterized it fully.
Jonathan Amos, BBC, you teased us with a picture at the beginning showing us a little impact site, and then you said nothing. So I was just wondering what was going on there. You thought you might have found the heat shield or something? There was some other item at the bottom of the picture that you scrolled down.
Yes, it was the heat shield, and then I wanted Mike to talk about that in more detail because he had better images from the MARTI of the heat shield deployment. Okay. So that was...
Okay.
That image actually shows, the fact that you saw the heat shield way off to the other side of that image shows you how high the vehicle was at the time the high-rise image was taken. And presumably the heat shield's falling pretty vertically, but you saw where the separation that you saw in the high-rise image was in fact an attribute of the angle at which high-rise was observing and the altitude at which the vehicle was. So that's why it was off at the bottom like that.
I understand that.
Now, I believe sometime in the next few sols, MRO is going to try to re-image the landing site. And both the high-rise and the context camera, which is my camera on MRO, will re-image the site. We'll look around for all the hardware that was a part of the vehicle as it was descending. It should be pretty close.
Hi, Bill Harwood, CBS News, with a very, very quick nuts and bolts question for Jennifer. Are all 6 wheels oriented parallel to the long axis of the body? There was one picture I confused myself. It looked like they were either clocked the way I wasn't expecting. I just want to make sure I understand where everything's pointed.
Yeah, they're all oriented in the,
Okay.
yeah, it may have just looked different.
Do we have any more questions? It looks like we're done with questions, so we will wrap this up for today. I do want to say, though, that all of the images and the animation are available on nasa.gov as well as jpl.nasa.gov, and I'll also give you the URL for the mission page is mars.jpl.nasa.gov/MSL. Any of those locations will take you to all of the images that you've seen today, and we will be back again tomorrow at 10 a.m. Pacific time, and broadcasters stand by for a replay of all of the images. Thank you so much for joining us today.